Our project is the design of commercial building in both conventional RCC and post-tensioning slabs and beams. The project members are K. Hemapriya, J. Meghala and Raisa Bernadette FG. Under the guidance of internal guide is Ms. Avi Aishwarya, MTech, Assistant Professor, Vailtech High Tech. And the external guide is Engineer Kalyana Sundaram, ME, MIE, Executive Engineer and PWD, Chepak. The aim of our project is to design a commercial building with RCC and post-tensioning slabs and beams. The main objective is to design the beams and slabs with conventional RCC and post-tensioning. While the conventional RCC beam and slabs are designed using StartPro software, while the post-tensioning slabs is designed using RAT software. This is the methodology of our project. First we collected the literatures, then we created a plan, then the model is created using software StartPro, and the properties are assigned. Then calculating the loads and analysis is done. The same procedure is repeated for post-tensioning structure. Our project site is at Chromepet, so we decided to do a soil investigation at the site. We carried out 2 trials, and the trial pit depth ranging from 1.85 to 2 meters. Then at the trial pits we decided to conduct a dynamic cone penetration test, while the output of the cone resistance was converted into the equivalent N values, while N is nothing but the number of blows required for the penetration of 30 cm of the split spoon sampler. 2 locations, one at the front side and another is at the back side. The test is conducted at a depth of 2 meters, while we required 100 blows for the penetration of 6 cm at the location 1, and we required 100 blows for the penetration of 10 cm at the location 2. As the soil at this level is identified as soft rock, no soil sample could be collected for the laboratory analysis. Then the bearing capacity corresponding to the shear failure and to the settlement is calculated. For the design purpose, the bearing pressure corresponding to the settlement is taken, while the value we calculated is 384.45 kN per meter square. So the bearing capacity of the soil is taken as 300 kN per meter square for the foundation design purpose. For this bearing capacity, the framed structure with isolated or combined footing can be provided. And this is the geometry of our building. The length is 48,100 meters and the breadth is 51,400 meters, while each floor height is 3.3 meters, while the basement wall height is 0.9 meter. This is our building plan, commercial building plan, and we developed a key plan for this, representing the location of the beam and the column with their spacings. With the help of this key plan, we developed a model using the StartPro. Our building contains 3 stories, ground plus 3, and the materials we used are, for conventional RCC, the concrete grade is M25 and the grade of steel is Fe415. And for post-tensioning, the concrete grade is M35 and the grade of steel is Fe415. And the grade of pre-stressing strand is 1860 Newton per mm square. And the rebar is HYSD bars. Next, coming to the slab design. The slab thickness is calculated using this span depth factor given in the codebook IS 456 clause 24.1. This recommends span to overall depth for the slabs having simply supported or continuous under cantilever. In our case, it is a continuous slab, so the corresponding span to depth factor is taken. And the slab design, while the span of the slab along the x direction is 3 meters, while along the y direction is 6 meter, and the depth of the slab to overcome both deflection and the bending moment is calculated, and the depth to overcome the deflection is 90 mm and the overall depth is 125 mm. The load is calculated using the code 456. The design is done, and the depth to overcome the bending moment is calculated as 45 mm. So the maximum depth along these two is taken for further calculation, and using this formula the AST required and the spacing is calculated. The AST along the x direction and y direction for both top and bottom reinforcement is calculated, and this corresponding spacing is also calculated. This is the layout of our slab. We used 8 mm dia bars at 315 mm spacing and 240 mm spacing along the x direction, and 8 mm bars at 450 and 600 mm spacing along the y direction. Next, the load calculation. The loads which could be applied for the grade beam is full wall load and partition wall load. Only the 50% of the load goes to the grade beam, while the 50% is taken by the soil below. The load is calculated using the formula unit weight into height of the wall into width. The unit weight of the brick is 220 and the height of the wall is 4.2. The width is 0.23. Similarly, for the partition wall, the width would be 0.115 meter. The next, the load acting on the beam, the parapet wall load, the full wall load and the partition wall load. This is calculated using the formula unit weight into height of the wall into width. Then the slab load, in this slab load the floor slab and the roof slab is calculated separately. For the floor slab, the dead load corresponding to the slab thickness it is calculated, and the flow finish of 1 km is given. And for the roof slab, self weight and the weathering course is added 2.5 kN per meter square. And the staircase load for both the dead load and live load is calculated separately. All these loads are applied to the elements for the beam and the columns, and the analysis result is taken. From this analysis result, the critical beam is identified and the design of this critical beam. This is the bending combined bending axial stresses. This is the design of the critical beam, and this is the shear bending moment diagram for the beam, and this is the deflection diagram. All these design results are taken from the StatPro software, and this is the design of critical column. This is the maximum bending and the corresponding design of the column. It's a bending moment and the deflection. These are the sections we applied for the elements for column and the beam. And coming up to the footing design, we design isolated rectangular footing. From the analysis report, the end support reactions are taken. For this maximum support reaction, we designed the footing. The loads coming up to the footing is calculated, and the depth of the foundation to overcome the bending moment, to overcome the one-way shear and to overcome two-way shear is calculated separately, and the maximum depth of these three types is taken as the depth of the footing. It is 1100 mm, and for these maximum bending moment and the deflection, area of steel required is calculated, and from this the dia of the bars is assumed and the spacing and the number of bars is calculated. is the layout of the footing representing the bar reinforcement. At the end strips, 2 number of 12 mm dia bars is provided. At the middle strip, 12 mm dia bars, 8 numbers is given. And that's all for the conventional RCC building. Coming up to the post-tensioning building, the key plan is modified by removing some of the intermediate columns under the beams so that we could get a larger span. This is the key plan for post-tensioning. For the design of the post-tensioning slab, we used a software named RAT, that is Reinforced and Post-Tensioning Analysis and Design Software. In this, the input given are the design code and the material we used, the reinforcement type, whether it is a bonded or unbonded post-tensioning, the member type, then the reinforcement cover, concrete strength of the concrete, and the depth. By giving all these input, we get a result output in the PDF form. In that, the span of the slab is given, that is 9 meter plus 6 meter, overall 15 meter span. All the columns are the knife edge, and the load cases we applied as self weight, inertial dead load, and the live load. A self weight of 5.63 kN per meter square is applied, and an initial dead load of 1 kN per meter square. Live load of 4 kN per meter square is given. And coming up to the load combinations, it is ultimate short-term service, permanent service, and deflection. All these load combinations by default it is applied, and this is a graphical representation of the load cases. And coming up to the design part is the design of pre-stressing. The profile of the strand is parabolic, and the steel diameter, the strand diameter is 12.7 mm. That type is a monostrand, and the anchorage size is 5, that is it can take up 5 strands, while we have provided only 4 strands in the anchorage. And the spacing of the tendon is 1 meter, while the top cover is 25 mm and the bottom cover is 35 mm. And this is the profile of a tendon. The above one is the allowable profile, and the second one is the adopted profile, which we adopted. And this is the graphical representation of our tendons. These tendons are provided along the bending moment diagram for their efficient purpose. Due to pre-stressing, a force is applied on the slab, and this is the tendon forces due to pre-stressing, and the below one is the bending moment diagram, and this is the shear force diagram. In pre-stressing, only 75% of the load is taken up by the post-tensioning, and the remaining 25% should be taken up by the reinforcement rebar. And that design for both the bottom and the top reinforcement is given in this table column for both span 1 and span 2. This is the slab tendon profile. While for the span of 15 meter, 4 strands at 1 meter spacing is provided, while for this 6 meter span, 5 strands at 925 mm center to center spacing is given. This is the rebar details, while the rods in red color are the bottom reinforcement and the green color of the top reinforcement. we have provided 10 mm dia bars at 150 mm center to center as the main bars, and 6 mm dia bars at 200 mm spacing as distribution bars, while for the bottom reinforcement 6 mm dia bars at 175 mm center to center spacing is given on both the ways. This is the post tensioning beam design. For this design, we used codebook IS 1343 1980. From this, the moment of resistance due to tendons is calculated using this formula. While the grade of the concrete is we used M35 for post tensioning, so FCK is 35, and the grade of steel FY is 415, while the grade of pre-stressing strand is 1860 Newton per mm square. The overall depth of the beam is 225 mm. Since we have provided all concealed beams, so we have provided the same depth of the slab for the beam also. The width of the slab beam is 1000 mm. And the tendon arrangements, we have provided 4 strands of 12.7 mm diameter, and the cover is 35 mm. So putting all these values in the above formulae, the area of pre-stressing steel is 395 mm, and the effective depth of the section is 176 mm. So the corresponding AST and the reinforcement bars are provided. Now calculating the stresses due to pre-stressing. The total effective forces due to pre-stressing is 1003 kN. So the stress provided should be less than these forces. The first diagrammatic is the cross section of the beam, and the second one is the direct stress, that is P by A. The next one is the bending stress due to the eccentric cable, that is due to pre-stressing, that is PE divided by Z. At the top it is ZT, at the bottom it is ZB. The next one is the bending stresses, that is M by ZT and ZB. Then the last one is the resultant stresses. And this is the beam tendon profile. This is also provided according to the bending moment of the beam. Four numbers of 5 strand is provided. This is the rebar layout for the beam, and this is the design result. For RCC, the critical beam dimension is a depth of 0.6 meter and the width of 0.3 meter is given. The AST is 610 mm square. For post tensioning, the beam is 225 mm depth and 1 meter width. AST is 395 mm square. While for slab, the depth is 125 mm and for post tensioning is 225 mm. And there won't be any changes for the column, while for RCC and post tensioning, the design procedure is similar. And the footing, for the footing design, the safe bearing capacity is 300, and the size of the footing we provided for the maximum reaction force is 3 meter by 2 meter, and the depth is 1.1 meter. And the corresponding AST and spacing is given. These are the literature we studied for this project. The deflection control in RCC beams by using mild steel and strip. The cost effectiveness of a post tension and reinforcement concrete flat slab system. Project based comparison between reinforced and post tension structures for sustainability perspective. And prediction of deflection in post tensioning slabs. the deflection of reinforcement concrete floor slabs. Comparative study of RCC and pre-stressed concrete flat slab. Analysis and design of RCC and post-tensioning flat slab considering seismic effect. And that's all of project. Thank you.